Today we're going to talk about factoring difference of two squares. So if we look at example number 1, we go through the whole process of is there a GCF, which there is not, how many terms there are, there's 3. So we can do quick factoring because A is 1, and if you're not liking the whole quick factoring A is 1, then make sure you always do A times C regardless. And you'll see that you get 4 and 4. So this comes out to be x plus 4 squared. Okay. If you look at the next example, a times c would be negative 16, but b would be 0. So what two numbers multiply to negative 16 and add to 0? That'd be 4 and negative 4. So we have x plus 4, x minus 4. Okay. And what we just did was a special case. Okay. If we drop down, remember that factoring is just undoing the distributive property. So if we look at this example, it says multiplying the following binomials. So this would be x squared minus 8x plus 8x minus 64. Notice the middle two terms cancel out and we're left with x squared minus 64. Okay, and then same thing if we look at number 3, this would be x squared minus 5x plus 5x minus 25. So x squared minus 25. Hopefully you're starting to see a pattern here that when we have x squared minus 16, that factored to these two because the middle term was 0. Well, when you multiply an opposite signs out of the same number, you see that the middle term cancels out. So this is actually known as the product of two perfect squares. So we call it the difference of two squares. Okay. And using just a and b, this would be a squared minus ab plus ab minus b squared. So this simplifies to a squared minus b squared. Okay. Now the big thing you need to remember is that this is the difference of two squares, not the addition of two squares, right? There's not a candy out there that's AOTs, there's only dots. So it's the difference of two squares, which means subtraction. Okay, so now if we look at this above, what is the reverse order? Well, it's going to be what we started with, a plus b times a minus b. And that's pretty much what we're going to practice today. So let's go to the next page. Okay, so first you need to look, is there a GCF? No. How many terms are there? There are 2 terms, so notice we are doing the last of the flow chart. And then you have to check to make sure that they're both perfect squares. And how we tell if they're perfect squares, well, hopefully you know your perfect square numbers by now. And if you look down here, 1, 4, 9, 16, 25, and so forth, you can fill that in later on your own on remembering square roots or perfect squares. And x squared and x to the 4th and x to the 6th and so forth. Those are also perfect squares. Basically, any even exponent is a perfect square. So in example 1, we do, and we just basically break this down to set it up as x plus 2 and x minus 2. So what number times itself gives you 4, and what number or variable times itself gives you x squared, x and x. If we look at the next example, these are both perfect squares. That's a 1 in front, which is a perfect square. X squared is a perfect square. 64 is a perfect square. And we have the difference. That is key. I didn't say that on the last example, but we have the difference. So that's going to be x plus 8 and x minus 8. Notice that we basically just took the square root of 64. Okay, and then in the final example, notice that we have a number other than 1 in front, but the same thing, just check to see if it's a perfect square, which it is. So we can break this up into our plus and our minus, and then basically the square root of 9x squared is 3x, and then 5, 3x minus 5. And as always, you can use the distributive property to make sure that you get back to the original answer. All right, let's go down. And what I want you to do right now is I want you to try examples 2 and 4 on your own. And then when you're done, check your answers. So go ahead and hit pause now. Okay, here's what we should have gone for our 2 answers. So both of those are perfect squares. And then go ahead and split it up into your plus and minus. All right, at number 5, so GCF, no, we have 2 terms. We look for the difference of 2 squares. In order to have the difference of 2 squares, we need 2 perfect squares, which we do. We need the difference, which we do. So we can go ahead and split this up. So 2x plus 7 and 2x minus 7. Okay, let's take a look at 6. So first question you ask yourself, is there GCF? And you've got to be really, really careful on these problems because notice that both 16 and 100 are perfect squares, but I can take a GCF out to start. So I must do that. Take out a 4, and I'm left with 4n squared minus 25. So that'd be a really good active note to take, that even if those 2 numbers are perfect squares, you still need to factor out a GCF. So we look inside the parentheses. How many terms do we have? 2. Do we have the difference? Yes. Are they both perfect squares? Yes. So 4, 2n plus 5 times 2n minus 5. All right, once again, we're going to try 2 problems on our own. So let's try 8 and 9, and then check your answers when you're done. So go ahead and hit pause now. Okay, so in number 8, there was not a GCF. You had 2 terms, so you look for perfect squares. Both 81 and 4 are perfect squares. And as you will see, there is a mistake on here, and I did that on purpose because oftentimes, especially it comes into play with the numbers 4 and 16 for some reason, we forget to actually take the square root of them. So this would be 9b plus 2 and then 9b minus 2. And the other thing that happens is with 16, sometimes people accidentally take the square root twice. The square root of 16 is 4, not 2. So make sure we know the difference between those. And then here is your answer for number 9. There was a GCF. You had to take out a 2x. Look inside. There was difference, 2 terms, and both were perfect squares. Okay. All right, let's take a look at 10. Notice with 10, we can first need to put it in descending order, in other words, standard form. Okay. And then hopefully we recognize there is a GCF, so let's take it out. Then we look how many terms are on the inside. There's 2. Do we have the difference? Yes. Are they both perfect squares? Yes. So we can continue to break this up as follows. Okay, and then in number 11, is it in standard form? Yes. Is it, is there a GCF? Yes. We need to take that out. make sure you take the negative out of everything. And this is one example that you had to also be careful in because both 4 and 36 were perfect squares. So you had to make sure that you check for the GCF as well. And then we can continue the problem. Okay. And just as a side note, you guys, you can still use the x factor with this. It would just be -9 and 0. And so the two numbers that would work were 3 and -3. Okay. But of course, if a is 1, then you would have, or a was not 1, you would have to do more work. All right, last example, is it in standard form? Yes. Is there GCF? Yes. Okay. And then I can factor this further, right? Wrong. Because the difference of two squares only applies to the difference, and this is addition. Okay, but this is not prime because we took out a GCF. Okay, remember that if you factor something, it can't be prime. An example of where it would be prime is, let's say, x squared plus 16. We don't take a GCF out in this example. And yes, x squared and 16 are perfect squares, but remember the whole part of difference of two squares is that the difference comes first. No difference. So this example would be prime. Thank you. Have a great day.